last time. We didn't formally state it, we'll do that this time. Okay. So the idea behind this algorithm is you try to do greedy, but then you allow for correction. Okay. And we said that this is one of the few problems where you can actually do that. So that's the idea behind Ford-Fulkerson's algorithm. And formally speaking, the way you do this is by maintaining what is called a residual graph. Okay, and this is what we spent a lot of time last class defining. Okay, so I'll just recap that. Okay, and so the idea is you have some flow f at the current step, okay, and you want to define this residual graph that just depends on this f. Okay, so we call this residual graph G sub f. So this is just a new network in its own right. Okay, so this is just a directed graph. It has some capacities. And the idea behind this algorithm was if you have some flow f, you build its residual graph G sub f, and you find some f prime in this residual graph, then turns out you can find a new flow in the original graph, which I'll denote by f plus f prime. It will be a valid flow and it satisfies all the constraints. And the value of that flow will be value of f plus value of f prime. Okay. So this is the main idea behind this algorithm. Okay, so we'll see this definition again, so you will understand this more. But this is the general idea. Okay, so you have current flow. Based on that, you form this residual. In the residual, you find an f prime. And then you can actually find a flow that's equal to the sum of these two. Okay. So valid flow in G. Okay, so this is what. Alright, so we defined the residual graph as follows. Okay, so maybe I have a picture. Yeah, okay. So I have a picture. So formally what we did was you have this flow F, right, and you have the original graph G. And what we are doing is, in G sub f, you will have two things. One is the forward edges and the other is the backward edges. Forward edges are simply the edges that existed before, okay, except that you will change their capacity. So if the capacity originally was C of E, now you will make the capacity C of E minus Fe. Okay, so if this flow F sent some Fe units of flow along that edge, then you will reduce the capacity. So the idea is that this is the leftover capacity for that edge, right? Because initially you could send certain units, initially it had some capacity, you used up some part of the capacity. Okay, so the C of E minus F of E is very natural. Okay, so, and then we also said something about backward edges. Okay, so let me get to that in a bit. So any questions about forward edges? So forward edges are simply, what you would have, in the sense that it's the leftover capacity. And this backward edges are where the novelty lies. So it's basically you introduce new edges, okay, and they go in the reverse direction of the original edge E. Okay, and its capacity is equal to the flow that F sent. Okay, and this is the thing that allows us to correct some flow that we already sent. Okay, so let's see an example. So in this example that we saw before, where the greedy algorithm fails, so suppose you did the greedy thing. Okay, so suppose F sent 1 unit of flow along these edges. So the capacity of these edges was 1, and you sent 1 unit of flow. Okay, so the remaining capacity along these forward edges is now 0. So that's what I wrote here. So the forward edges have capacity 0. And additionally, we introduce these backward edges, right? And these backward edges now have capacity 1. Okay, so the capacity of these backward edges is the amount of flow that you send. So this is the residual graph for that flow F. Any questions about this? Okay. Alright, good. So let's see why. Yeah.
So will we be introducing backward edges in the existing path, like not in the other?
Say that again?
So there is an existing path, right?
Yes.
On the top side. So we'll be introducing backward edges only in the existing path.
What do you mean existing path?
I mean there is a flow path.
Right. There is some existing. There is some flow at this point F, and you'll introduce backward edges for every edge in that flow. Okay, so every non-zero edge in that flow. So, yeah. So if your flow was more complicated, if your flow had both these things, then you would have lots of back edge. Okay. And the way this allowed us to make progress was now once you introduce these back edges, then you could find a flow in this residual graph, which basically went like this, and this is a new flow, and this is f prime, let's say, and we defined this notion of f plus f prime, where we actually we cancel out edges if one had a forward edge and the other had a backward edge. So this is what we defined last time. And f plus f prime will satisfy all the original capacity constraints. Okay, so it will be a feasible, is a valid flow in G. So that was a nice thing. Okay, so it will satisfy all the original capacities, and you can convince yourself that this will be true. And the value of this flow will actually be the sum of value of f and value of f prime. So that's the nice thing about this this residual graph. You find some flow f prime on it, and then you can find a better flow in it. Alright. So this is the motivation behind this Ford-Fulkerson algorithm. Okay, so this is the main property that we are using. And the idea is you start with f equals 0. Okay, so there's a base flow where you have, it's just the original graph. And as long as there exists a positive flow f prime in this residual, you just set f equals f plus f prime. Okay, so you increment f with this new flow f prime. But this, as I wrote it, is kind of a chicken and egg thing, right? So on this, how do you start this algorithm? You're saying initially the residual is the graph itself. You're saying first find some flow and move along. So why is this okay?
Is it because you're just doing a greedy approach first?
Yeah, so essentially all you're doing here is you're finding some bigger than zero flow. Okay? So you're just seeing if there is a non-zero flow possible. You don't have to find the maximum flow, right? Just find some non-zero flow and add it to f. Okay? Then find the new residual, find a non-zero flow there, and so on. Okay? And how do you find a non-zero flow? Because a flow is a complicated thing, right? How would you find a non-zero flow? Yeah.
You find something going out of the source that's non-zero.
That's how you can start, but it has to go all the way from S to T, right? So how would you do that? I mean, so what is the simplest flow you can think of? Like, suppose I give you a network, and I tell you that there is at least one unit of, suppose all the weights are integers. Suppose I have to tell you there is at least one unit of flow you can send from S to T. Okay. So how would you do that?
You just do a breadth first search.
Yeah, you do a breadth first search and you find just one path, right? And if there is no path, then there is no way there could exist a flow. Okay. So to find some non-zero flow, it's actually enough to find just one path. Okay, so that's the idea behind this. Okay, so there is a bigger than zero flow if and only if there is a bigger than zero path. Okay, and path is like a directed path now because this is a directed graph.
I have a question.
Yeah.
This might be stupid, but why wouldn't it be better to do a depth first search because you just need to find any path, and so you just do depth first to find the first one and take that?
Yes, you could do any search, but we'll see in a bit why breadth first search is actually better. Okay, so it's a very good point. So hang on to that thought. Okay, so it's you could do any search at this point. Okay, at this point, any search will work, and all you have to do is just find a augmenting path. Okay, so this is easy. Oh, sorry. By the way, I think I didn't define. So such a path is called an augmenting path. Okay, so because you are using it to augment the flow, right? So that's why it's called an augmenting path. Okay, so this is the algorithm. Okay, so just before we go, it's you start with the zero flow, and you see if there exists a path. So this is like what greedy is doing, right? So you see if there exists a path. But now you move to the residual. Okay, so you compute this residual flow and see if there is a path in that graph. If so, you add that, and now you have a new flow. Compute the residual for that, and keep going. So is the algorithm clear?
Well,
Yeah.
the only thing that's not clear to me is the path in the residual is not available in the original, so.
Right. It's not available in the original, but f plus f prime will be valid in the original one. So that's the theorem that we.
Visually what that means.
So f plus f prime, maybe I should, so I defined it last time, but basically what it is let's say you have some flow, right? So this is too simplistic, so let me draw a little bit more complicated one. So you have, okay, so these are some edges, and maybe there are more edges in the graph. And so initially, let's say you had some flow, right? So actually maybe I should draw the residual. Okay, so suppose the original flow was something like this. Okay, so it was here, and it also had a little bit of flow which went like this. So I'm drawing this example. Can you see this, by the way?
Yes.
Okay. So in this example, what's happening is, my original flow is a bit more complicated than that. Okay, so there it was just one path, right? So here the flow consisted of something that goes along this path plus something over here. Okay. That's still a flow because this is something depending on the capacities, right? So suppose this was the case. So in this case, your residual graph will have back edges like this, and it might have some other back edges and so on. So now what you're saying is, if I use the back edge in an augmenting path, then how do I go back and make it a legitimate flow in the full graph, right? So that's what you're asking.
Yes.
So the point is, so the capacity of the back edge was only the flow that you already sent. Okay, so that's the idea. So the capacity of the back edge is so this is how the residual was defined, right? So the capacity of the back edge is only the flow that you already sent. Okay, which means if you used that edge, okay, in your new path, the most flow you could have sent on that edge is Fe. Okay, so it is possible to legitimately cancel out the original flow you sent but you can't have a negative edge, basically. So that's what this is saying. Okay, so if you look at any edge, so initially you send some flow Fe. In the residual graph, and let's say this had capacity C of E. Okay, in the residual graph, you'll have a forward edge of capacity C of E minus Fe, and a backward edge of capacity Fe. Now, if you use that backward edge, the most capacity you could, the most flow you could have sent on that backward edge is Fe, right? And let's say you even sent Fe, then it's like saying you cancelled out the backward path, right? So the forward, so if in your new path you end up sending Fe units of flow along the backward one, then it's like saying in the original graph you just sent, you sent 0 forward. Okay, because, so you should think of it as flow in the original graph as being, so for F prime of E, you can think of it as being minus Fe or something like this. So F plus F prime at this E will just be 0 in this case. So think about this for a second, but this will make sense. Okay, so if you had sent a flow in this F prime, in this residual graph, and along an edge that wasn't already present, okay, just think of it as a negative flow and add them up numerically. So it will turn out that you will get no negative values, okay, and that you can verify. And you will get values that are all at most the capacity. Okay, because you can only use forward edges, and there the capacity was lower. Okay, so if that's still not clear, is that somewhat clear, vaguely?
Yeah, I think so.
Yeah, so basically think of I think that's the easiest way of thinking about F prime. Think of it as if you are using a negative edge, if you are using an edge that's not there in the original graph. Okay, if you are using a back edge, think of it as having F prime of E minus Fe, okay, and then add them up numerically. Because of the fact that the negative edge has capacity on the Fe, you could not have sent more than Fe units of flow. Okay, so you'll never have negative values. Okay, so that's what this is saying. So yeah, that's a very good question. So it's I actually encourage all of you to go back and draw pictures and draw examples, okay, because that's the only way you understand these things. Okay, so it will make a little bit of sense if you see this, but really if you draw an example, it becomes very clear. What's going on is very simple, but it takes the edges going backward, forward, and so on. Okay, so you've got to think about the scheme.
As we go through the algorithm that we were on the latest slide that wherever we were, are you going to have negative values along the way, and then eventually when you're done, obviously you won't have any, but
yeah, so that's the nice so the abstraction we are doing is that at every step you have some flow F that's feasible in the original graph G. Okay? So the argument is not any iterative thing. Okay, so the algorithm is just one step to the next, and because F plus F prime is a valid flow in G in the original graph, okay, so what we have is that at the next step you are basically back in the previous situation. Okay, so you just have a new flow, but it's a valid flow in the original graph. You're not constantly changing the graph. Okay, so your graph G is the same. It's just your residual that's changing. Okay, so the flow values and the residual is changing at every step. Okay, so that's why this argument has to be for any valid flow in G. Okay, so for any valid flow in G, you do this, and then you will come up with a new valid flow in G, whose value is value of F plus value of F prime. Then in your next step, your argument will just be about G and this F plus F prime. Yeah, so this is one thing that you've got to, I guess, realize when you're making an argument, that you want to have a general enough statement at this step so that you can just keep reusing this argument. right? Because you don't want to keep changing the graph as time goes on, because that will create, like you'll have forward negative edges going on all over. Alright, good. So any other questions? Okay, so let's quickly see why this is, why this is correct. Okay, so today I will show you one proof, and in the next class we'll see a slightly different proof that actually gives more insight. Okay, so we'll see the slick proof this time. Okay, and this will hopefully also answer some of the questions he mentioned, because here we'll define a new operation which is minus. Okay, so this is a bit more tricky than the previous one. Okay, so if you understand this, then you'll hopefully understand what's going on. So what this is saying is, so first the statement of the theorem, right? So what the theorem says is, suppose you have any flow f1. Okay, think of it as the flow that you have right now. Okay, and suppose the flow is not the maximum flow, okay, which means there is some f2 such that value of f2 is bigger than the value of f1. So you take any flow that's not the max flow, then in the residual there is always a valid positive flow. Okay, so in the residual there is this flow which we will call f2 minus f1. I have to define what it is, and its value will be val of f2 minus val of f1. It's kind of like the plus, but now it's a minus. Okay, so it's defined the same way as a plus. And this flow will be valid in the residual graph. Okay, so firstly, suppose I could prove this. Okay, so I haven't defined what this thing is, but suppose I just prove that there is a flow of value val f2 minus val f1 in the residual. Then I claim we are done. So why are we done?
It's like
Yeah.
rearranging of the flow, right? So previously we claimed that residual graph is equal to f1 plus f2. Now we are like rearranging.
Yeah, so that's essentially what's going on. But the point is that this value is bigger than 0. Okay, so and so what this implies is that there is a non-zero flow in the residual graph, right, between S and T. Okay, because this value is strictly bigger than 0. And as we said before, as long as there's a non-zero flow, there should be a path. Okay, so there has to be an augmenting path. Okay, so is this point clear? So what this lemma implies, what this property implies, is that if you are not optimum, the residual will have an augmenting path. So that's what this says. So this, maybe I have that. Yeah. So the implication of this is that unless your current flow f is the maximum flow, there is always an augmenting path. And let's see why this is true. Okay. So firstly, how do I define this f2 minus f1? So this is actually as you would expect, right? So f2 is some flow. Okay. So note that f1 and f2 are both flows in G. Okay. So there are no backward edges or anything in f1 minus f2. Sorry, in f2 minus f1. Okay. So these are the original edges of G. And each guy has a non-negative flow on these, right? So maybe there is an f, suppose this is the edge E that we care about. Okay. So here there is an f1 of E and there is an f2 of E. So the way you define f2 minus f1 is, if f2 is bigger than f1, then it is the same thing. It's the forward edge, right? It is a flow of value f2 of E minus f1 of E. And if f2 is smaller than f1, then again you do the natural thing. Okay, so if f2 is smaller than f1, okay, so this is case f2 bigger than f1. This is case smaller than f1. So in this case, what we do is basically put some value of flow on the negative side, okay, on the backward edge. Okay. And why should the backward edge always exist?
What's the classification?
So we should claim that the backward edge exists in GF1, right? G sub F1, in the residual graph for F1. Okay. But residual graph for F1 always has a backward edge of capacity at least F1. And we are saying that F1 is actually bigger than F2. Okay, so that's this case that we are in. F1 is bigger than F2. F2 was always non-negative, so F1 has to be strictly positive. Okay, so this backward edge has to exist. Okay, so backward edge always exists in this case. So let me write down this case separately so that it's clear. Less than F1. Okay, in this case, backward edge has to exist. In G sub F1. Okay, because this is the residual. Residual has a backward edge whenever F1 has a non-zero flow. Okay, so it will exist. And F2 minus, and the weight you will put on this backward edge is basically F1 of E minus F2 of E. And by definition it's non-negative. Okay, because this is, in this case, F2 is smaller than F1. So this new flow on the backward edge is feasible. So note that when I'm talking about feasibility here, I am skipping the flow conservation. Okay. The reason I'm doing that is because it's actually trivial, right? Because if F1 and F2 both satisfy flow conservation, F1 plus F2, F1 minus F2 will satisfy flow conservation. Okay, so that's why I'm not talking about conservation. I'm only caring about the capacitance. Okay. And so what I've argued here is the capacities in this F1 minus F2 are actually valid. So in this F2 minus F1 are actually capacity constraints are satisfied. So this is actually a valid flow in the residual graph. Okay, so G sub F1. Is this clear? So I expect that, yes sir.
That case, should that be F2 of E less than F1 of E?
Yes. This is, everything is, I'm arguing on an edge by edge basis, and that turns out to be the cleanest way to argue. So if this thing is not clear, just go back and draw some examples. Okay, so many times these kind of flow arguments are subtle. So even if it seems clear, I would encourage you to go back and do it, because you'll realize that maybe you missed something, and it's like I keep missing stuff in these kind of things all the time, right? So it's even after so many years, so it's normal. Okay, so I would encourage you to go back and work out the details. Okay. But this is a rough idea, okay, that this F2 minus F1 as I have defined is a valid flow in this residual graph. Okay. And this implies that unless you actually are at the maximum, you can always find an augmenting path. This means that the algorithm is correct, because if the algorithm stops, it means that it could not find any more augmenting paths. and that means it's actually the maximum. So this again, if you think about it, this is the same argument we always use to prove something is maximum, right? You say, suppose it's not, consider something else as maximum. You say that the algorithm could have improved or done something. So it's the same argument. It's just now it involves all these residual graphs and so on. Okay. So let's move on. Okay. So let's move to the running time. So all right. So what's the running time of this algorithm? So how would we go about analyzing this? Actually, how long does computing an augmenting path take? Like one step of this, right? So this was the algorithm. You start with f, and you say while there exists an augmenting path f prime in G sub f, okay, you find that path and then you set f prime f equals f plus f prime. Okay. So this somehow so this step is what we need to first analyze. So and this step essentially consists of computing G sub f and trying to find an augmenting path. Right? So how long do each of these take? So given a flow, how long does computing G sub f take?
Size of the flow.
It's the size of the flow, which you can also worst case bound it as just O of m, right? So it's you're right. If the flow is much smaller, this could be much better. But in general, if you had a dense flow, then this is the easy upper bound. I'm computing G sub f. And how long does it now take to compute to see if there exists an augmenting path? So augmenting path is basically some directed path that goes from S to T, right? So in this new graph, you want to see if there is a path from S to T. Okay, how long does that take? This is directed paths, come on, we should, all of you should be shouting out the answer to this. Yeah, it's m plus n, it's actually, there's no log n here because it's just paths, there's no shortest. So, not yet. So this is m plus n. So this is nice, right? So every step takes m plus n. Okay, but how do you bound the number of iterations here? Like this is the other common thing that shows up, right? So when you have an algorithm that's making progress, you've got to be able to quantify how much progress you're making, right? So that will bound the number of steps it can take. Okay. So it's like, at every step, the total flow you have, the value of the flow is only increasing, right? And it can't increase forever. So how much can it increase to? Yeah, so if the max flow is actually C, then, and all the numbers are integers, then it can only increase from 1 to C, like in steps of 1, right? So this gives a very easy bound of O of C times m plus n. So C is the value of the max flow and m plus n. But note that this is, yeah, okay, so this is nice. So let's maybe pause here for a bit and then I'll tell you why this is bad, why this is unsatisfactory.
But C could depend on the degree of your S and T.
It will, yeah, it could depend on the degrees.
So if it's a very dense network, then it could be a contributing factor to your runtime.
Yes. So C, I'm saying there's actually an even worse problem. Okay, so yeah.
If you have reverse edges,
Yeah.
then you could end up having paths with cycles.
Path with cycles, yeah, sure. I mean, it won't happen in the max flow, but in principle, yes.
So in GF,
In G sub f?
yeah.
Yeah, that could happen. Yes.
So you might end up considering every single edge multiple times.
that's fine, but that's the usual problem, right? In any, whenever you want to find the path from S to T in a directed graph, you will have this kind of problem, right? So that's why in DFS you never, once you visited a vertex, you don't visit it twice. So this is nothing new compared to what DFS has to do, right? That also has to work in any directed graph. Okay, so you could have cycles. Cycles are not a problem. You don't explore things twice. No, this is a perfectly valid algorithm and this is a perfectly legitimate running time. It's just that C could be extremely large. Okay, so that's what I'm saying. And by large, I don't mean n or something polynomial, but in terms of the input size, it could be extremely large. Okay, so that's the thing that we'll consider. Okay, so remember, even in knapsack and these kind of things, if you remember your homework, you had one question where you say, what is the input size, right? Most of you probably thought it's a trivial question, which is true. But the thing to note there was that this C could actually, I mean, it will depend on the capacities of these edges, right? So let me give a very simple example. Okay, so consider this graph. So in this graph, what's the max flow value?
2C.
It's 2C, right? So max flow is 2C. Okay. And what is the input size?
Log of C.
Yeah, it's just 4 times log C or whatever, and it's log of C O of this, right? This is how much space you need to write out what the input is. Okay. But now in this graph, suppose I tell you there's an algorithm with running time O of C. Okay, so that's what this tells you, right? It's m plus n. M and n are constants here. So the algorithm has running time which is O of C, let's say. Okay. So that's actually exponential in the input size. Okay, because the input size is only log C. Okay, and your flow is, your flow is exponential in the input size. Yeah.
I'm sorry, what is the input in this case?
So yes, that's a good question. So so input basically is, so imagine you have some graph, and how do you represent it, right? You have one maybe some unit of memory. You have some n which tells you the number of nodes. Then you have some adjacency matrix probably, and you have this weight matrix, right? So in this weight matrix, you write down C, you write down this 1, and you, okay. So how much memory do you use in this process? So if C is, let's say C is 10 to the power of 30, then the way you write down the C is just 1 followed by 30 zeros, right? So it only takes 30 amount of memory to write down. Okay, so that's what I'm saying. Okay. So to write down the input, it takes only O of log C. Okay. While your algorithm has running time which is C, which is exponential in this input side. So this is actually something of concern. And so even otherwise, as you were saying, maybe the C is relatively big, right? So maybe it's even a polynomial, but it's fairly big. Okay. So that's still bad for us. So let's see if this kind of running time is actually the best possible. Okay. So one question to ask is, okay, so maybe my analysis is weak, right? So this is something you should do for when you're trying to analyze any algorithm. Okay, so you come up with some analysis, you get some running time bound, then you've got to think, okay, is there a better bound that's possible? Okay. And in this case, it turns out the answer is no. Okay, and the reason is, this is actually a cute example if you guys haven't seen it before. So here, initially, so suppose I did some, I guess he asked the question, what if I just do depth first search, right? And maybe the ordering was such that I found a path like this. Okay, so this is a fully valid path, right? And from this I will construct a new graph. Okay, so this will be S. This is the so the residual graph for this flow is you have C minus 1 here, and you have an edge 1 here, and an edge 1 in the opposite direction, not drawing the zero edge that goes forward. Okay. So if you want, there is a zero edge that goes forward, and there's C here, that is C minus 1 forward and 1 backward. Here there is C forward. Okay. So this is the residual graph for just this one flow. And now you could be pretty unlucky again, right? So now I want to find the augmenting path in this flow, in this new network. So maybe you found this path, this squiggly path that I'm drawing. Okay. This path you can also just send 1 unit of flow because there is a 1 edge, right? So maybe for those who missed it, if initially if I found this path, then I can only send 1 unit of flow along this path because there is an edge of capacity 1, right? So I can't send more than 1 unit. So that's why this was this resulted in that path. Now in this graph again you are unlucky and you can only send 1 unit of flow. And so what's the resultant flow here? So maybe this example will illustrate some of the things that you are asking. Okay. So in this case, the F plus F prime that we compute. Okay. So this one had a forward edge, this F had a forward edge and F prime had a backward edge, which is at mid edge. So they both cancel out.
You keep getting that.
Yeah. Yeah, so basically F plus F prime will be the flow which looks like this. It will have 1 unit going here, 1 unit going here. Okay, so this looks like what we want, but it has only 1 unit, right? Now, if you look at the residual for this F plus F prime, okay, it will actually be the same graph but with C minus 1. Okay. And if C was, I don't know, 10 million or something, then this keeps happening and you'll have 10 million iterations. Okay. So this is the bad example. Okay, so this says that it will actually take two C iterations. To get to optimum. Okay, so this is so as such the algorithm is not. I mean, it could take so long, and you've got to find other things. Okay, so is this example clear? So for those who want to understand this, so maybe try to figure out why F plus F prime is this. Okay, so then you'll realize what's going on. So good. So this is looks like a bad example. So how do we? I guess all of you can now see what we did wrong, right? So what did we do wrong in this kind of an example? So
We used the path with the weight 1 first.
exactly, yeah. So we ended up. I mean, we could have been smarter. Maybe we could have said, you know, instead of picking any path, pick a path that can give you the most flow, right? Try to be greedy in that sense, right? So maybe you pick a path that has as much flow as you can, okay? And what that means is basically every edge along that path has to have a highway. That's one thing to do. So it turns out this actually works, okay? So there are actually 2 ways to get around this problem. Okay, we won't. Maybe we won't see them even next time, but we might see one of them next time. And so the 2 ways are actually both things that you guys have pointed out in the past. Okay, so one is what he just said, which is, you know, every time you have a choice, pick the path that has the most flow. Okay, that ends up giving the most flow. So this you can do. How do you do this?
With breadth first.
I mean, you've got to keep track of the flow values, right?
Shortest path.
You can modify shortest path algorithm to do this. Okay, so it turns out. But another easier way to do this is to guess the value. I mean, see how much flow you could possibly get. Okay, so I mean, in some sense, so suppose I tell you that I want a flow of at least some delta. Okay. So then I could throw out all edges that have capacity less than delta and see if there is a path. Right? And then I could do a binary search for delta. So that's a very simple way of doing this. And other thing is you can also modify shortest path. Okay, so that's the other way of doing this. But in general, this can be done in m plus n log n. So this you can convince yourself. And this is nice because this leads to an overall running time of m plus n squared. It's not so great, but it's okay. Right? So that's what this gives. The other thing is what again you were saying, which is suppose you do breadth first search, okay, to find the augmenting path. Then you'll find the shortest augmenting path in terms of the number of steps. Right? Turns out this is also fine. Okay? And if you see this example, one of the reasons this was failing was because you found a path of length 3, not a path of length 2. So this is actually, yeah, this is a little bit trickier to see why this would actually give, I mean, it would get around this issue. Because maybe there are short paths, but they also give slow improvement. Right? The point is it can't always happen. So, alright, both of these give rise to something like, I think this actually gives n times, it only gives something like n log n iterations, I think. Okay. I'm not sure, actually do you guys know? I think this is only n, right? Okay, anyway, I can confirm this next time. Okay, so this leads to only something like much fewer iterations. Okay. I think this is the mn squared argument. Right? This is yeah. Anyway, so we'll but it definitely leads to polytiming. Okay, so it's either m plus n or n, and so in this kind of line of work, there is big. I mean, there's generally a lot of interest in reducing the running times because these running times are actually pretty bad, right? So here, if I use this, it says the number of iterations is of, I think this only leads to m plus n squared or something like this, and here it leads to O of n iterations. So, okay, what I analyzed here is the cost per iteration, but I think that's the known bound even on the number of iterations. So you want the number of iterations to be as small as possible, okay? And so trying to figure out how many is actually a very interesting question. I think you can get something like square root n iterations. So I will talk about that next class. So there are a whole bunch of algorithms that work on, that basically try to find the best augmenting paths you can add so that your number of iterations is very small. Okay, so we have 15 minutes and I want to, no, we have maybe like 20-25 minutes. I want to spend a couple of minutes on this thing this question which I guess all of you saw in the homework. So this is this problem of maximum matching. Okay. So suppose you have a bunch of people. So this is actually a simpler version of this. Okay. So where you have only 0, 1 weights. Okay. So you have a bunch of people and you have a bunch of objects. And every person has a value for the object, right? And suppose the values are just 0, 1. Okay, so he either likes that object or he dislikes that object. So every person has a subset of objects that he likes. And this guy maybe likes this and this. This guy likes this, and so on. Now, you've got to assign objects to people so that as many people receive objects they like as possible. So the goal is the same thing, which is maximize total happiness. So you guys all know what's going on, right? So I'll just write maximize happiness. Okay. Otherwise, I'd have to write something more complicated than is necessary. Okay. So basically, so a person is happy if he gets a gift that he likes, and you want to maximize total happiness. I claim that this can be written as a flow problem. So do you guys see how this is how this could be done? Have you already seen it?
No.
Oh, okay, then go on. Yeah.
You have a source that goes into all the people and a sink coming out of all the objects.
Yeah, great. So you will have a source here and a sink here, okay. And I want to assign as many, I want to make as many people as possible happy, right? So in some sense, this suggests that, okay, I should have, and I'm counting every person the same way, okay? So I'll have edges of capacity 1 that go like this, okay, that go out of S. And now, if a person likes an object, you put a directed edge like this. And then you put edges from here to here, all of capacity 1. So now, if you want to find the maximum amount of flow that can go from S to T, so what you've got to do is pick as many, so you want to send flow along as many of these edges as possible, right? So, okay, so let's say I want to have a total happiness value of some C, okay? So then I've got to send flow along C of these edges. I could also send fractional flows, but for now let's say I always send 0-1 flows. So one of the cool things about this previous algorithm is that if you had integer values, it will only find integer flows, and it was guaranteed to find the optimum. Okay, so what this proves implicitly is that there is an integer flow which is maximum. Okay. So if you didn't understand that, never mind. Okay, so assume that you have an integer flow is the maximum. Okay, so you've got to send 1 unit of flow along C of these edges. Okay. And now there is flow conservation, right? So each of these guys has to get something. Okay, so this will end up happening. So you will send some flow along one of these edges. Now, so far this was okay, right? So one object could have received multiple incoming things, okay? But that's not valid, because then if you wanted to have flow conservation, you would have had to send 2 units of flow along this, okay? So there was no way you could send flows back, right? All edges were directed forward to back. So this guy, if he had to, if his capacity to T was only 1, then it could have gotten matched to only one of these people. So that's why this is actually a matching, okay, or this is actually a valid assignment. So that's the argument. Okay, so the max flow is equal to the max total happiness. Okay. So this is the This is one very simple application of flows. Okay. Turns out there are many applications of this. So next time we'll see what's called a cut problem, and we'll see how flows and cuts are they have a very nice relation between them. Okay. And that will also help us move towards this whole notion of duality. Okay. So we'll see that after the break. So this slide was to that. Okay. So I will stop here with what I want to do. So the last 15 minutes I want to spend at least 5 minutes doing this, and then maybe a little bit of review. Okay. So I guess we don't have much time for review, but let's do the final project. Okay. So some of you seem to have noticed. So on the course web page. On the course web page, there is now a link to possible project topics. And this is simply a list of papers. So this is simply a list of papers where hopefully you can find all of these in a downloadable way. Okay, so I think there are about 25 papers. And as I said before, so most of these papers are classic. Some of them will be difficult to read. Okay, so it depends on how challenging you want your project to be. Okay, and so the point is, so if for the ones that are difficult, you may want to use other online resources. Okay, so pick one of these papers, send. So first the other thing is. You are allowed to pair up. Okay, so the project is in pairs. You don't have to, but could be done pairs. Okay, so you don't have to pair up, but you are allowed to pair up. And if you do, you can just submit one report. Okay. And for papers that are tricky, and there are some papers here that are more involved than the others. Okay. For those things, you can use online resources. Okay. So some of these papers, so the way in general computer science evolves is that people find some way of first solving a problem, and then many others simplify this approach. Right. So you could actually find explanations of a paper that are easier than the paper itself. Okay, so look for those also. Look for lecture notes and so forth online. And but you've got to discuss that paper. Okay, so not do a completely different thing for the same problem. Okay, and so discuss with your partner and so on. Okay, so this is the general thing, and. Some people asked if they could do a completely different project, not reading a paper and writing about it, but do some kind of implementation. So for this, do talk to me and get permission before basically the week after fall break. So you can think about whatever you want to do during the break or something, and then you can come back. So if you want to do something else, talk to me beforehand. Okay, so don't. You can't come in the last minute and say, okay, I did something else. Is this okay, kind of a thing. Okay, so do talk to me or the TAs before this. Okay, so how would you write this project? So as I said, this is supposed to be a very short summary. Okay, but it's supposed to be 2 pages long. Each of these papers will actually be, most of them will be significantly longer than 2 pages. So you've got to figure out what the important things is. And the goal of this project is, it's essentially to read some of the classic papers. Okay, so that's the main goal. The other thing is, when you read a paper, how do you identify the important points of it? Okay, so that's the thing I want you to get from this. So some of you, has anyone here taken this class that Suresh offered last semester? I guess it doesn't apply to newcomers, but about how to read a paper. Okay, you too. Maybe maybe some of you may have taken it. So I don't know if does he have any notes for that?
I think so.
Okay.
He has notes on his.
Okay. So, yeah, but I guess it's not useful, right? Because solution for how to read is not to read more. Anyway, so all right. So let me tell you what we are looking for in this. Okay. So what I want you to look at. So when you read a paper, first thing you've got to get out of it is what problem they are trying to solve. Okay. And this is the first thing you've got to figure out. And the other thing is, why is this paper significant in the broader context, right? So you've got to figure out why this problem is important, and some background on why why it's important, some motivation or some background on what people have done about this. So this is the second thing. And the third thing, often, there are some papers that don't do anything very difficult, but most of the papers I've listed, they actually have they solve problems that are intrinsically difficult. Okay. So I want you to identify a little bit as to why the problem is difficult. Okay, so this is very subjective, and in some sense this is optional, in the sense that it is nice if you can point out something like this, but I understand, some papers, it might be very hard to quantify this. Okay. So, and this is kind of related to the importance, because sometimes problems are important just because they're difficult, right? So that's one thing. And then you should identify what the main result is, and this is related to the problem statement. So oftentimes there will be a broad problem statement that they want to solve, and they'll achieve some partial progress towards it. Okay, so you've got to figure out what the main result is. And almost all the papers I've tried to put in only papers that have some algorithms in them. Okay, not just some complexity theoretic results or something like this. So try to write down what the main steps of the algorithm are. Okay, so this is you could call in some sense the approach. And you have to write down a little bit about the outline of the proof. Okay. So this again is a tricky part. So I probably have a slide on this. Yeah. So this is again, this is the thing that you've got to develop. Learn to figure out. Okay. So oftentimes, especially in theory papers, the algorithm will be somewhat inspired by the proof itself. Okay. So that's one thing in which theory papers and more applied papers differ. Okay, so more applied papers usually just come up with the algorithm, and then they either don't prove anything about it, or they prove something minor about it. Okay, so but theory papers, usually the algorithm itself is motivated by the proof. Okay, so in that sense, the outline of the proof is very important. So I want you to be able to identify that. Okay, so this is. So of the lot that I have here, apart from this why difficult, this is probably the thing that needs the most explanation. Okay, so I'm going to let's go into detail. So yeah, so the basic point is you've got to give. You should be able to identify the main lemmas in the proof. Okay, so often the proof will have. You have some algorithm and you want to analyze it, right? So the proof will say, oh, okay, to analyze it, I will simplify I'll first analyze this, that implies such and such, and once you have that, then it implies the final thing. And there could be multiple layers like this. So the point of this outline is to essentially identify these lemmas. Most well-written papers do this themselves, but some of them you'll have to work. Okay? So try to identify the main conceptual lemmas, and then go to why they imply the main result. And many of these papers will have lots of result, so it's okay if you focus on what you think is the main result. Okay? And just mention that there are other results which they also consider. Okay? So this is the thing. And So one thing you should remember is that this, the write-up that you produce should be self-sufficient in the sense that you can't, don't refer to, lemma such and such and so forth in the original paper. Okay, so if you are referring to something, just restate the main lemmas if you want to. So, and in some sense, the way it should read is, if someone's willing to believe you about the statements of these lemmas, then they should be able to see the proof. So, yeah, so the details you don't have to go into, but just the key statements are useful. So, yeah, so let me stop there. So I don't have much time for review, but we can, so there's specific things that you feel, I mean, I guess we've covered a lot of ground in this, in these first few weeks. So, are there specific things where you felt that, maybe some more detail would have been good? Like, I think some of the more recent stuff, I have intentionally not gone into the full details because, going into details won't give you too much more intuition. Okay, so the idea was to give you some insight but not detail. So any other topics like this? So, so far I guess the important things we've done, which you should all know, is the basic paradigms, of course. Okay, so that's what's dynamic programming. This hopefully all the homeworks have, in the homeworks you got a good sense. And yeah, NP completeness and so forth, you should know what NP completeness is, how you prove, how you reduce one problem to the other and so forth. And with graphs, we saw a bunch of algorithms that were relatively easy. Okay, so in the sense that you do the natural greedy thing, but then you do something clever to optimize the running time a little bit. Okay. So that was the style of the shortest path algorithms, spanning trees, and so on. So the one interesting thing we did here is flows. Okay. Flows were also natural, except for this idea of a residual graph, which allowed you to correct a greedy state. Okay. And that's what you should remember out of flows. Okay. And yeah, so the initial stuff, recurrences, divide and conquer, they are just basics. At this point, you should all be very comfortable with that. Okay. So that's what the summary. So going forward, so I'll have to change this a little bit. So we'll have one more week of flows, matchings, and cuts. Then we'll go into randomization, and that's actually the cool stuff. Okay, so it's things which are as, most of them are as fundamental as the other things. Okay, so it's and they are also more broadly applicable to things that you will face, I think. Okay. So questions about if you have specific things that you haven't understood, feel free to contact me or the TAs, and we should be able to go on. Okay, so I just want to know if there's some topic where many of you thought, yeah, so actually if you thought there was a specific topic where maybe spending a little bit more time is useful, let me know. I'll try to do some session before maybe before we start off next time. Yeah.
Will you and the TAs be answering questions on Canvas over the break, or?
I will be.
Yeah, I will also be around, so mostly around. I might answer in a delayed way, but
Okay.
I might disappear for a few days, but
yeah.
I'll be there most of the time.
Alright, see you guys, have a fun break.